Welcome back to the Deep Dive. And for you, our number theory students, we're jumping back into the OEIS.
That's right, the online encyclopedia of integer sequences, an amazing resource.
Absolutely. Today, we're looking at sequence A000007. It's titled Integers of Form x squared minus 2y squared. You know, when I first saw this one, I thought, okay, simple formula, but there's clearly more to it. What makes these numbers special? That's what this deep dive is about.
And what's really fascinating, I think, is how such a seemingly straightforward algebraic form by 2y2, it reveals some quite deep patterns within the integers themselves.
Okay.
So our goal here is really to quickly get a handle on what these numbers actually are, how they behave, and, what their significance is in number theory.
Right. Let's unpack that. So A000047, specifically, it's counting the number of integers.
Yeah.
Integers less than or equal to 2 to the power of n.
Correct.
That can be written in this by 2y2 form. The sequence starts 1, 2, 3, 5, 8.
Which sounds simple enough.
It does. And these were listed by N.J.A. Sloan himself.
Yeah.
In the original handbooks.
Indeed. And to make this a bit more concrete for you listening, let's take a 3.
Okay.
The sequence entry there is 5. That means there are 5 integers less than or equal to 2 cubed, which is 8.
Right, up to 8.
That fit this x squared minus 2y squared pattern. And those numbers are 1, 2, 4, 7, and 8.
And they come from specific pairs.
Yeah.
Like x and y values.
Exactly. So 1 is 1 squared minus 2 times 0 squared. 2 is 2 squared minus 2 times 1 squared.
Yeah, 4 minus 2.
4 is 2 squared minus 2 times 0 squared. 7 is 3 squared minus 2 times 1 squared.
9 minus 2.
Got it. And 8 is 4 squared minus 2 times 2 squared. That's 16 minus 8.
Wow, okay. That helps. But it does raise the question, finding those XY pairs feels a bit like guesswork. Is there a rule, some underlying property, to know if a number can be written like that?
Ah, you've hit the nail on the head. Yes, there is a rule, and it's actually quite elegant.
Oh.
It all comes down to prime factorization.
Okay, primes again. Always primes.
Always primes. Basically, an integer n can be written in the form x squared minus 2y squared if and only if. In its prime factorization, no prime that's congruent to 3 or 5 modulo 8 appears with an odd exponent.
Whoa, okay. Hold on. Primes congruent to 3 or 5 modulo 8 raised to an odd power.
That's the key. It's a beautiful connection, really. It shows how these quadratic forms are deeply tied to the arithmetic properties of primes.
So it's like a filter based on primes.
Exactly. It tells you precisely which numbers belong in this set just by looking at their, let's call it their prime fingerprint modulo 8.
Prime fingerprint, I like that. Can we break down that modulo 8 condition a bit more? Like, what does 3 or 5 modulo 8 mean practically? And the odd power thing.
Sure. So modulo 8 just means looking at the remainder when you divide by 8.
Right.
So primes like 3, 11, 19. They leave a remainder of 3 when divided by 8. Primes like 5, 13, 29. They leave a remainder of 5.
Okay.
Now, take a number, say 6. Its prime factorization is 2 times 3.
Right.
The prime 3 is, 3 modulo 8. And its exponent here is 1, which is odd.
Okay, odd exponent.
So according to the rule, 6 cannot be written as by 2y2. And you can try. You won't find integer x and y that work.
I see. But what about, say, 18? That's 2 times 3 squared.
Good example. Again, we have the prime 3, which is 3 mod 8. But this time, its exponent is 2.
Which is even.
So the rule doesn't forbid it. And indeed, 18 can be written in this form. It's 4 squared minus 2 times minus 1 squared. No, wait, let's use positive y. 18 is 5 squared minus 2. 6 squared minus 2 times 3 squared. 36 minus 18.
Got it. So 18 is allowed because the bad prime, 3 mod 8, has an even exponent.
Precisely. It's like those primes, the 3 mod 8 and 5 mod 8 ones, are only problematic if they show up an odd number of times in the factorization.
That's a really neat rule. Does this kind of modulo condition appear for other quadratic forms too? Or is this specific to the minus 2y squared part?
Excellent question. Similar principles apply to other quadratic forms, but the specific primes and the specific modulus, like 8 here, depend on the form itself. So the minus 2 is definitely important for getting this particular rule involving modulo 8.
Right.
This whole area connects to deep work by people like Shanks, Schmid, Borvine, studying which numbers are represented by which forms.
And you mentioned computation earlier.
Yes. What's great is that this prime-based rule makes it computationally feasible to check if a number is in this sequence. You don't have to search for x and y.
You just factorize and check the exponents of the 3 mod 8 and 5 mod 8 primes.
Exactly. And people like Seth Troisi have actually implemented this efficiently in C++ and Python. It shows how theoretical number theory can lead directly to practical algorithms.
Very cool. So wrapping this up then, for our listeners exploring numbers, We've taken a quick journey through A000047.
Mm-hmm.
We identify these integers of the form by 2, 2y2. And the key takeaway really is this shortcut. Check the prime factorization for those specific primes modulo 8 with odd powers.
Right. And connecting this to the bigger picture, I think this dive shows that even simple-looking algebraic forms hide these elegant underlying structures governed by primes.
Definitely gives you a new perspective.
Which leads to a thought for you to ponder. If we understand these rules for specific forms like by 2 to y2 so well, how might that deeper understanding help us unlock maybe bigger secrets? Perhaps about how prime numbers themselves are distributed, or maybe even find new structures within integer rings. What could these specific patterns tell us about the grander landscape of numbers?